Hi, everyone. Thanks so much for coming, and thanks for bearing with all of the technical issues. So we are finally ready to get started. I'm going to go ahead and introduce Bonnie Wang, who's going to be the sessions chair for this machine learning and cloud computing track. So just a reminder that talks are going to be 15 minutes long, and we're going to say 2 minutes for questions since we're a little bit short on time. And Bonnie's going to be holding up like 10-minute, 5-minute, 1-minute warnings for you guys. So just please keep that in mind. Thank you. If you could just have the first speaker come up.
All right. Good morning, everyone. My name is Ryan, and I'm going to talk about a joint project with my advisor, Sindhu Kali, exponential family prediction markets. And here we are going to study the trader strategy in this kind of market. So first of all, let's look at this picture. This picture was taken in 1998. It was a picture where there was a great flood in South China that year, and which caused an economic loss over $30 billion. So, and also over 4,000 people lost their lives. So one very important lesson from this disaster is that the government should be able to aggregate information before the disaster happens so that it can better prepare and prevent the possible loss. So naturally, we want to ask these two questions. So who needs the information and who has the information? Of course, the government is the one who really needs the information, but just to name a few who has the information, the people who live near the river, and also people who are experts studying this river, and also like just the weathermen. All these very dispersed population can have information. So one way to aggregate such information is to use a prediction market. And prediction markets are not just in academia. It actually exists in real life. So look at this. This is a screenshot that I took yesterday. It's the Iowa electronic market, which has a market on US presidential elections. And the price of the stocks traded in this market, just roughly speaking, represent the market consensus of the likelihood of a candidate is going to win the election. And Google also has had its internal prediction market several years ago. This helps its management to aggregate information from its employees that is otherwise maybe impossible due to like corporate politics or hierarchies. So formally, prediction markets are a tool for information aggregation. And in this market, people trade contracts based on the outcome of future events. And we also refer to these contracts as securities. And the price of these securities are just reflect the current market prediction of the event outcome. So how do prediction markets work? We start from a function called scoring rule. The scoring rule takes your prediction and also the final event outcome and then produce a score. That is basically how good is your report is. So suppose that we are going to have a prediction on whether it will rain in Cambridge tomorrow, and say, I believe that there is an 80% chance that it will rain, so I report 0.8 as a probability. If it actually rains tomorrow, then I get a score of log 0.8. If it actually not rain tomorrow, then I get a score of log 0.2. This is when we use a logarithmic scoring rule, and there are a whole lot of scoring rules other than that. One very important notion here is the proper scoring rule, which basically says I have the incentive to honestly report my belief in order to maximize my expected profit. So, but scoring rules are good, but they don't really look like markets. So one way to do this is use a cost function-based market maker. So this way, we have a centralized market maker in the market, and the traders will trade with the market maker only. For example, we have the market maker maintains a cost function. Its argument is going to be the number of outstanding shares in the market. And if we differentiate that cost function, we get the price function of each security. So basically, still continue with that example. Suppose you have a market which has two securities, basically. One represents it will rain tomorrow. The other one represents it will not rain tomorrow. And suppose the market starts with 0 shares for each of the securities. And the current price, according to that price function, is going to be 1/2 for each one. Suppose you, as a trader, you come into the market, and you want to buy 1 share of the security that represents it doesn't rain tomorrow. Then what you're going to pay is the cost function of the the final state of the market minus the cost of the previous state of the market, in which case this is going to be log of e plus 1 over 2. So this is good because it actually turned out that such cost function-based market maker are entirely equivalent to the scoring rule that we just mentioned. So that after all, we'll just work with the cost function-based market maker. But one thing is, remember that prediction markets are all about information aggregation. And sometimes this definition is vague because how do you characterize such aggregation process? And we use a market framework called exponential family market, which basically offers a mathematical characterization of the aggregation process. So why do we want to use that? Basically, exponential family distribution has a PDF like that. And there is a very nice correspondence between the components of this distribution and also the components of prediction markets. For example, the payoff function is going to be equivalent to the sufficient statistics, and the number of outstanding shares is going to be equivalent to the natural parameters and all these other things as well. So basically, the exponential family distributions encompasses a lot of, a huge family of distributions, and most common distributions that you see are a member of this family. Yeah, for example, there's the normal distribution, which is also going to be the one that we do simulation later on based on this normal distribution. So under this general market framework, we use a specific market model called where we assume that each trader is risk neutral and also they are Bayesian traders. So what do we mean by that? So basically each trader has a private sample and they have the same sample size but maybe different sample mean and variance. Say this particular trader comes into the market and she has a private sample of size M and mean mu, and then previously, there are n traders traded in the market, and market price is new. So her trading decision is going to be a Bayesian update process. It's basically, she will buy that exact number of shares so that to move the market price to this weighted average of the previous market price and her own sample mean. Then it comes to our results. There are several key features of prediction markets that are particularly interesting, but one that actually lies at the heart of the issue is incentive compatibility problem. So in prediction markets, this incentive compatibility problem refers to, say you are a trader and you are incentivized to report your own belief honestly and promptly. But we also mentioned that proper scoring rule just basically ensures that we want to do that honestly. And we also mentioned that the cost function-based market maker are equivalent to scoring rules. So didn't we have already solved the problem? Well, actually no, because the traders can trade repeatedly, and then a strategic trader might be able to see some opportunity in not being truthful and achieve a better profit, maybe by misleading other traders to do this. So every model needs assumptions, and here are our assumptions. We assume that we only have two traders in this market, T1 and T2. Still under the Bayesian market framework, we assume that they each have a private sample of same sample size, but different sample mean. And they also have a strategy. So the strategies are a partition of the sample size, which basically means, say, 2-4 is the pair 2-4 is a strategy. That basically means so you are going to report 2 of your data points in the first trade and 4 of their data points in the second trade. So to actually get to the results, we just briefly mentioned some analytical results that we proved. So basically what this says is that, first of all, we can assume that the traders trade alternately. And then it is another very strong theorem is that under our assumptions, the market always achieves information aggregation. That is, the final market price will be average of the traders' their respective sample mean and also the initial market price. But the question here is whether such aggregation process is efficient. So here we use a simulation approach. First, we generate 2 traders' samples, and then we also generate the initial market price. After we have generated all these, then we just run simulations, tens of thousands of simulations on different trader strategies, and then we compare the profit for these different strategies. So in our first simulation result, we further assume that the second trader, T2, will always be truthful. The reason why we don't assume that T1 will always be truthful is that when T1 is truthful, then no matter what strategy T2 takes on, then T2 will only trade once in this market. And by the properties of scoring rule, then honest strategy will always be the optimal one. But when T2 is honest, then things are a lot more complicated. So in all these 4 graphs, the horizontal axis represents the number of data points that T1 reveals in her first round of trade. And so, which basically means here we have a sample size of 50. Then if T1 is going to report 50 data points, then that's equivalent to the truthful strategy. So in the first picture, we show that holding everything else equivalent for these 2 traders, then the truthful strategy is actually going to be the optimal strategy for trader 1 on average. But this result is nice because we have a monotonistically increasing expected profit. But if we actually tweak this model a little bit, in the second picture, top right picture, we assume that T1 has a greater sample variance compared to T2. So one intuition is that when you have a greater sample variance, that basically means you are not so sure about your belief. And then just think of just a financial market. When you are not so sure about your belief, you should not be trading so aggressively because you may possibly be wrong. And here, actually, the result corresponds to this intuition is that T1 should, in this case, report as few data points as possible, just roughly, and there's some minor issue there, but just generally report as few data points as possible in the first trade. And similar pattern occurred in the bottom left picture. In the bottom left picture, we return to the initial assumption, but then we assume that T1 sample mean is very far from the initial market price. So the intuition here is that if your belief is very different from the market's price, then either you're wrong or the market is wrong, but more often it's just you're wrong. And then it's common sense that you shouldn't be trading so often in the first place. But one other thing to note is, in addition to the curves on the graph, we also have a histogram, the blue bars, and that represents the optimal strategy in each round of simulation. So as we can see, in all these cases, there is no all-time optimal strategy, and that is even in the first case, the honest strategy is not always the best strategy. So that basically implies that there is virtually no hope in finding an analytical result about the optimal strategies. And further, we complicated our model to allow for 2 random traders. That is, T1 and T2 will both pick a random strategy, a uniformly randomly strategy, and then we compare their expected profit with what will happen if they had used an honest strategy. And the results are similar here. There is So in the first plot that is holding everything else the same, then T1 is still better off being honest. And T2, as the second trader who is going to trade in the market, actually has the opposite conclusion. That is, T2 should not trade honestly. And that's some kind of interesting. And also when we just tweak the T1 sample variance and also the sample mean, then we get exactly the same direction of the result as we did when we assumed that T2 is always going to be honest. So just a summary of this presentation. First of all, prediction markets are very useful tool for information aggregation, and especially from a very dispersed population. And the market mechanism have already been very well studied, and especially for the exponential market framework. We also did simulation based on and verified this results. That is also a part of our project, but we didn't really have the time to show that. And another thing is incentive compatibility lies just at the heart of all information aggregation process, because you want the information that you get be true and honest. So our project just basically showed that you cannot find a deterministic result. Like all-time best strategy is going to be either the honest strategy or some other strategy, and we showed that no, there's no all-time optimal strategies. But our simulation shows some pretty interesting results that actually aligned with our intuition, and that's basically suggests some few next direction of the research is going to be actually investigate how this kind of stochasticness impact the trader's optimal strategies, and that's gonna be what we work on later. And thanks for your attention, and I'm gonna take any questions you have. All right. Yeah.
What potential applications do you think this could have outside of the general, outside of what we talked about? Like what future applications do you think?
Yeah, there is actually a very nice correlation between prediction market and just general machine learning. It is in another piece of work in 2014, someone actually showed that you can convert under some mild conditions, you can convert any prediction market into a machine learning problem. And equivalently, you can convert any machine learning problem into a prediction market, and you run simulation on this prediction market, then you actually solve the machine learning problem. And there is even a very nice parallel between just this kind of prediction market and also the no-regret learning, online learning. And so basically, you equate the traders with, you equate the securities traded in the market with experts. And then you want to minimize, in the prediction market, you want to minimize the maximum loss, potential loss that the market maker might sustain. And then in the online learning problem, you want to minimize the regret. And that's basically a very interesting parallel, and it actually has suggested some applications.
What applications do you think this could have in biotechnology and health and medical field?
I don't think at this point there's going to be a...
Mathematics or some type of understanding of how cancer or how this molecule inhibits this enzyme, like what potential do you think it could have in healthcare?
Frankly speaking, I haven't think about the applications in healthcare, but there has already been some applications in like peer review process, just the academic submissions. And there's going to have been some, like, when you submit to a journal and then you have all these other authors rate the quality of your work, and then you can implement a market on that so that you can like reduce the effort of having like reviewers to actually review your submissions, and that's going to be more efficient than the current process. All right, thank you so much.
So my name is Christina, and I will be presenting our work on developing an interactive facial expression training platform for individuals with autism. So as an outline, I'll be going over what motivated our work, other related work, and the main components of our platform, which is real-time emotion computing, the EmoTrain interface, and a platform evaluation. So why were we motivated to design a platform for individuals with autism? So a couple of months ago, me and my research team visited Goodwill Day Services, which is a nonprofit organization that is focused on helping individuals with developmental disabilities such as autism. And after a lot of discussion with many of their patients and participants, and hearing a lot of the challenges they face, we decided to develop a platform that would help alleviate, hopefully, some of the challenges that they face. So as an overview, autism, for those of you who don't know, is a group of developmental disabilities that is characterized by deficits in areas of social interaction, communication, and language, and causes severe difficulties in perceiving faces, and particularly facial expressions. Currently, 1 out of every 68 children in the United States suffer from autism, and there are currently 21 million individuals with autism in the world. So our platform is aimed at helping those individuals in recognizing facial expressions and also performing those facial expressions. So I'll be detailing the design of implementing real-time facial expression recognition on a mobile device, designing the EmoTrain interface, and evaluating the effectiveness of the platform. Some related work are Affectiva, Let's Face It, and the Trust Borders, which all were computer-based intervention programs which showed great promise, since they showed that even with short-term intervention, a lot of those skills and emotion recognition can be improved in people with autism. So the core component of our platform is the ability to ask a user to perform facial expressions and teach them how to perform them. So the main functionality is real-time emotion computing, which the emotion computing model that we constructed is based on convolutional neural networks, which are one of the most effective deep learning structures. And as an overview, there are two basic components to CNNs, which are the forward pass estimation mechanism and the backpropagation mechanism. So while a neural network is being trained, during the forward pass estimation mechanism, an emotion prediction is obtained based on the input image, and that is compared to the image's label, and a loss of estimation is measured. And during the backpropagation mechanism, the CNN parameters are updated based on that loss estimation. So in order to create a very good emotion classifier, we needed a large and balanced data set, and because a lot of the available data sets were either small or unbalanced and led to many emotions being hard to detect, like anger and disgust, we collected our own data set. So the process for collecting our own data set was using a pre-trained CNN and fine-tuning it with images collected from the web, and then creating a game tool to collect face images, which from those images that we collected, we fine-tuned a CNN and created our emotion classifier. So the model is able to predict 7 basic emotions in a face image, which is angry, surprised, neutral, happy, disgust, fear, and sad, and assigns the emotion with the highest probability as a label for that image. So in order to be able to do this, to achieve real-time performance, we constructed the following framework, which included an application on a mobile device that would access the built-in camera and perform face detection, a web service that would receive those face images, and an emotion computing server which ran the model that we detailed earlier and computed the probability of each of the 7 emotions. So the EmoTrain platform, again, is designed to help people with autism to learn how to recognize emotions and learn how to perform those emotions. So as stated earlier, people with autism have severe difficulties in understanding facial expressions and also responding appropriately to others' emotional states. So the platform is designed to is as a game and will give users a face image that they have to mimic. And why mimic? Because previous studies have shown that training in facial expression mirroring also helps not only in learning how to make those expressions, but also how to recognize expressions. So this is a screenshot of the EmoTrain platform, where we see that on the right-hand side, a user is given faces that they have to mirror, and as we see, our work in real-time expression tracking is used for the platform to judge if the user is performing that emotion correctly. So in order to gauge the effectiveness of the platform, an evaluation was performed where 9 participants that were diagnosed with autism received training with EmoTrain for 20-minute sessions for 2 times a week for 2 weeks for a total of 80 minutes. Before the participants received training, and after they received the training, they were given a pre- and post-assessment where that consisted of 2 sections, which in the first one, they were just asked basic questions like what kind of gaming preferences and feedback on the platform, and a second section which gave them an expression recognition task consisting of 14 images that they were asked to identify the emotion of, which we can see on the right. So the first thing that we used to gauge the effectiveness of the platform was looking at their scores before the assessment and after the assessment. And as we see, for most of the participants, their post-assessment results are higher than their pre-assessment results, which shows that most people were able to recognize expressions better than after they finished training. And we also looked at the scores that the game would give the user while playing. And the purple is the scores that they received on their first training session, and the blue is the scores after their last training session. And as we see, there's significant improvement in their scores from the first time they received training and the last time they received training. So as a summary, EmoTrain is a platform that teaches individuals with autism how to recognize emotions and also how to perform these emotions. And the core component of this is real-time emotion computing on mobile devices as Android and iOS. And our platform is available on an iPad, iPhone, and an Android phone. And we also performed an evaluation which showed that the platform is truly effective. Thank you. So any questions? I'm sorry, another.
Other crossover fields,
Um,
parallel with the autism understanding?
So, well, other than being used as a platform for helping people with autism, while it's also a data collection tool at the same time, because the more people that use our platform, the more images we are collecting. And basically, it's also being used as an automatic labeling tool, because if a user performs an emotion that the platform asks them to perform, then we can automatically label that image as that emotion. Yeah.
Is there any future compiling that you guys are looking forward to doing that's outside of the general emotions that are normally expressed in autism?
I'm sorry?
Are there any future directions as far as advanced compiling of emotions that are outside of the general realm that you look for in autism?
Yeah, so future directions are also using this for patient monitoring, such as tracking pain in hospitals.
Awesome.
Yeah.
So have you watched the show Lie to Me, or have you heard of it?
I have heard of it.
So it's just more for like comment. It's a show, and they use like the muscles in the face to kind of show the different emotions. So just wanted to point it out. If you watch it.
Hi. So you said you're doing real-time, pretty much computer vision, right? And I was wondering if you could go more into how are you doing that computer vision and that analysis, what tools are you using and such?
Yeah. So we have a mobile application, and we use OpenCV to just do face detection, and we send 2 frames per second to our server, which then runs each image through the emotion computing model, and then sends back the result to the app. Yeah.
Thank you.
You said that you get the emotion stuff off of the images. Well, what if the person has a facial deformity, like maybe like a burn across his eyes, or maybe like just something that makes him look more angry when they're not trying to be? Would you be able to detect something like that?
Actually, we've never tested with anyone with facial deformities, but the game is created so that it's easier for a person to score, because we are compensating for the fact that the emotion prediction is not 100% accurate. So there's a predefined threshold for each emotion. So for harder emotions like angry or disgust, if you make above 40%, then you score.
Hi, great work. So in terms of training for the 7 emotions, I'm curious, what accuracies did you get when you were doing the training?
It's an 81% accuracy.
Okay.
Yeah.
I really like that you've combined the game aspect with this. Do you plan on making more games involved in the same type of platform, or just playing using this game and maybe enhancing the prediction model? Or?
Yeah. So we are looking into different. So we are looking into gamification as a tool of data collection. So we are looking into creating different types of games that can help us label and collect data for emotions and other facial expressions. Yeah.
Thank you.
So I was wondering if you had any problem when training pretty much your classifier, if you had any overlap or lower accuracy in emotions that are similar, such as surprised and happy, and how you dealt with those.
So yeah, because originally when we first created the model, we used available data sets, and we realized that a lot of emotions were underrepresented, like disgust and angry, which is why we created our own data set where we basically just gave everyone, all the students in my professor's class, to play the game, and we would ask users to specifically perform the emotions that were very little represented in our data set.
Thanks.
Okay, thank you.
Hi, my name is George Boateng, and I'm from Dartmouth College. And this work I'm about to present, I worked on it for my senior thesis in June this year, under the advice of my professor, David Coates. who is a professor of computer science at Dartmouth. And so for this work, I worked on an application, Stress Aware, which is a real-time stress monitoring application on the Amulet wearable device. So this Amulet wearable device was built by my professor's research lab at Dartmouth. According to the American Medical Association, stress is the cause of 60% of all human illness and disease. Stress can trigger recurrence of addictive behavior such as unhealthy eating and smoking. As a result, there's a need to monitor stress continuously, unobtrusively, and in real time. And knowing when, why a person is under stress could enable in the moment interventions as well as personal stress management. And so in this work, I developed Stress Aware to address this issue. So a bit of an overview of what I'll be talking about. So a few questions that I'll be trying to answer. Can we actually build an application to do real-time stress monitoring using only heart rate information? And will this application run for a very long time before needing to be recharged on this wearable device? And also, will people actually be interested in using this application? So to start off, the Amulet wearable platform is a wrist-worn device. It's a hardware and software platform for developing energy and memory-efficient applications. It has two processors. One is for running applications, and the other is for Bluetooth communication. And the board has a bunch of peripherals and sensors like a buzzer, accelerometer, among others. And it's useful for creating M-Health applications because M-Health applications need to run for a long period of time as they collect physiological data, so maybe for hours and days before needing to be recharged. And that's why this platform is very efficient for that. So about the science of stress. Stress is a physiological response to mental, emotional, and physical challenges. And when a person is stressed, the hypothalamus signals two systems in the body, namely the hypothalamic pituitary adrenal system and then the sympathomedullary pathway system. The HPA is responsible for long-term stress response, and it deals with the secretion of cortisol, which is a stress hormone, which is present in saliva, urine, and we can actually infer stress by looking at a person's cortisol level. The SAM is responsible for short-term stress response, and that deals with the autonomic nervous system, which has two parts: the sympathetic nervous system, which is responsible for increasing the heart rate of a person when a person is stressed, and the parasympathetic nervous system, which reduces the heart rate of a person when the stress period ends. So having said that there's actually a cardiac response to stress, we can actually infer that a person is stressed by looking at their cardiac activity, which is captured by an electrocardiogram. So an electrocardiogram is what you see in the picture over there. And heart rate is the number of R peaks in a minute in an electrocardiogram. And then RR interval is the time interval between the R peaks. And heart rate variability is a variability in RR intervals. And it deals with the relative activation between the sympathetic nervous system and the parasympathetic nervous system. And so we could actually possibly be able to distinguish between the stress levels of people by looking at their heart rate variability. So some work that has been done in the area of stress study. So one work was conducted by Haley and Pickard, and their goal was to determine a driver's stress level while driving. And for that, they collected various physiological data like ECG, EMG, and they were able to build a classifier that distinguished between low, medium, and high stress with about 97% plus accuracy. The second study was conducted by Etten and others, and their goal was to infer stress using a custom-built device which they called AutoSense, which measured various physiological data like ECG, GSR. And they obtained data from up 20 plus subjects, and they had an accuracy of about 90% with lab data. So these studies go to show that, again, physiological signals could actually be used to determine the stress levels of individuals. So Stress Aware, the app that I developed, it monitors a person's stress level in real time. It uses a machine learning model, which I train offline, and also uses data from a heart rate monitor such as the Zephyr, which you see in the picture over there, and then it classifies the stress level of a person, low, medium, and high, and displays the stress level over the past few hours as a bar graph on the screen, and also logs that to an SD card. So the various components of the Stress Aware app. So the first is the ecological momentary assessment, which is responsible for intermittently asking the subjects about to rate their stress level as well as the activity level. And the data that is collected from this is used as ground truth for training my machine learning model. The second component is the data collector, which is responsible for collecting heart rate and RI data from a heart rate monitor such as the Zephyr. And again, this data is used in training the machine learning model. And the third component is the stress detector. And that's what is responsible for actually determining the stress of a person. So what it does is that it computes a feature vector of a 60 seconds window of heart rate and RI data. It scales the feature vector, and then the stress classifier then uses the feature vector for the prediction. So the stress classifies an implementation of a prediction model of an SVM, which again I'll talk about that later. So the other component is the stress level graph, which displays the stress level of a person over the past few hours. And the last is the data logger, which logs to the SD card. So I evaluated the energy efficiency of the Stress Aware app. And to do that, I ran the app for 8 hours while it computed stress every 5 minutes and logged the battery voltage. After graphing it, the battery voltage dropped from 100% to 98%. But when I looked at the screen, it had dropped to actually 92%. So that represents an 8% battery loss per 8 hours. And so a projected battery life of about 12 days before needing to be recharged, meaning that the app is pretty energy efficient. So the stress detection model. So my goal was to develop a model to classify into low, medium, and high stress. And to do that, I used a support vector machine, which performs classification by constructing a high-dimensional hyperplane. And one reason why I use SVM was because a lot of literature has mentioned that it's been popular for mining physiological data. And so I trained 2 SVMs, a linear SVM and then radial basis SVM. And I use scikit-learn library for my machine learning. So I used data set from 3 sources. The first was from Physionet, which is a public database of physiological data. I extracted heart rate and RI data, grouped the data into 3 stress levels, and split the data into 60 seconds windows, which previous studies have said are useful in terms of inferring stress. The second was from a field study, which I ran. The field study was approved by Dartmouth's Institutional Review Board, and for that I collected data from 10 subjects who wore the amulet and the Zephyr for 8+ hours a day, as the amulet collected heart rate, RI, and then acceleration data. The subjects were prompted to answer 2 questions about their stress level and then the activity level. And I used data from 4 subjects for my machine learning training. I also ran a lab study, which again was approved by Dartmouth's Institutional Review Board. I collected data from 2 subjects, and the subjects were subjected to 3 stresses. So they were asked to do mental arithmetic, plunge their hand into cold water, and were started with a clap sound. And again, the amulet and the Zephyr collected various data, and they also rated their stress level, which was used for the machine learning. For features, I extracted various heart rate and heart rate variability features. The heart rate features that I extracted were mean, median, standard deviation, 80th and 20th percentile of heart rate. And then for my heart rate variability, I extracted mean, median, standard deviation, max, mean, 80th percentile of RI and others. And for the results, I had 3 experiments. So one was on the Physionet data set, and for that, I wanted to figure out if the effect of different feature sets. So I had 4 feature sets. One was heart rate features only, RI features only, features that are aggregate over several values, and then all the features. And for my results, features that are aggregate over several values had the highest accuracy with 94.5% accuracy with RBF. And for all the results, RBF performed much better than linear SVM. So the second was to figure out if acceleration has an effect in terms of the accuracy. And so for that, I computed an additional feature, which was mean of acceleration. And doing that, the accuracy improved from 89% to 100% for RBF, which shows that acceleration improves accuracy, which makes sense intuitively because an increase in heart rate could actually stem from an increase in physical activity rather than stress. So incorporating acceleration information would be useful in having a better accuracy. So the last experiment was the lab study data set. And for that, I had an accuracy of 50% for linear SVM and 64% for RBF. I couldn't really infer a lot because I had limited data for this. I also evaluated the usability of the amulet platform. Again, there are 10 subjects, 3 men and 7 women. And 80% mentioned that it was easy to answer questions on the amulet, which goes to show that there's a huge potential for using wrist-worn devices for EMA studies as opposed to the current methods, which entail using smartphones. Also, 70% mentioned that they would actually use the amulet and Zephyr to automatically measure their stress level. And 60% said that they participated in the study because of an interest in stress monitoring. All of this go to show that there's actually an interest in people in stress monitoring and that the amulet has the potential to be used by people. So some limitations of this work. So in terms of the heart rate variability features that I use, I didn't use any frequency-based features because doing those entail computing fast Fourier transforms, which are computationally intensive. So in the future, using those could help improve the accuracy. Also, the Zephyr doesn't report medical grade heart rate and RI values. And also the stress detection model that I used in my app was a linear SVM rather than an RBF, even though the RBF performed much better. And that was because RBF is much less memory efficient and also computationally intensive. Also, we didn't really test from new data from the wild, and also we didn't collect data that could be used to infer the cause of stress. So in the future, collecting data like location, noise level, or sleep duration could help also diagnose why a person is stressed. And also, we use only a small number of subjects, so in the future, having more subjects would be useful in terms of having really conclusive results. So to conclude, in this work, I developed Stress Aware, which is a real-time stress monitoring application on the Amulet Wrist1 device. The machine learning results that I had were 94.5% for the Physionet data set, 100% for the field study data set, and 64% for the lab study data set. For the battery life results, I had 12 days, projected battery life of 12 days before needing to be recharged. And the usability results show that there's a real interest by people in stress monitoring. This goes to show that the Stress Aware app has the potential to be used by people for stress monitoring, as well as to be used for stress-related interventions, and eventually to be used to improve the health of people. Finally, acknowledgements. I'm really grateful to Professor Reinhardt, who was really instrumental in terms of the thesis work that I worked on, and to Dr. Sarah Lord, who is a professor at the Geisel Medical School, and she helped draft the IRB protocol that was approved, and to the Amulet team that developed the Amulet platform and continue to support it currently, and also to Ghana Pope, who ran the lab study from which I got my data, and to the volunteers who participated in my study. And this research was funded by a grant from the National Science Foundation. Thank you.
Since you're doing it mostly on heart rate, how do you handle exercise, walking fast to class, things like that?
Yeah, so that's what one of the experiments that I actually did. So for the second experiment, so I tried to I computed an additional feature which was mean of acceleration, and including that in my feature set helped improve the accuracy. And so including that would help kind of differentiate heart rate stemming from activity as opposed to heart rate stemming from stress.
So I know that there are currently wearables on the market that claim to monitor stress levels. What makes this different from those?
Do you know could you mention any that?
I don't remember the name. I know because I've looked into buying them. They're supposed to they tell you to take a deep breath when you're too stressed and all that stuff. Okay.
Yeah. I've seen apps on smartphones that claim to monitor stress, but I haven't really seen on a wearable. So my first instinct is that these claims are not really validated in terms of peer-reviewed research that has been conducted. So when I see things like that, my first instinct is that somebody created an app that they think monitors stress, but until I see some kind of paper that references the work that they do, it's hard for me to believe. And in terms of this work, even though I feel a bit good about this work, I still don't feel really great because I think we'd need really more subjects and more experiments before we can actually say that we really have something that's really great at stress monitoring.
Thanks.
I had an interest in this topic, but something interesting that popped up is athletes, not while they're doing extraneous work, but after years of doing extraneous exercise, their entire physiology as it pertains to stress and stress management is increased significantly. So, can you see your device solving that problem, seeing higher stress levels than normal, but that's okay for many, Olympic athletes?
Okay. Again, to address that issue, I guess having a lot of data from a wide variety of people and also possibly incorporating person-specific information could also help address that issue. So exploring, like including something really specific to athletes, some aspect of their physiology, including that into the feature extraction could help address that issue.
I was going to ask quite a similar question, just like on the other end. What about people, because I know that heart rate can vary between 60 to 80 beats per minute in the average person, and for some people like myself, it's even higher, like 90 beats per minute. How does the device sense stress in people whose heartbeats are a little bit out of the range, or even within the range, like 20 beats per minute is quite a big gap?
So right now, one way to address that issue would be to kind of normalize the data over different people, but I'm not really doing that in this study over here. So that would be another future direction. So normalizing the data, seeing how that affects the effects of that, and also, again, incorporating more data from a wide variety of people would also be useful in terms of addressing that.
Thank you.
Yeah.
So we saw in the results that the RBF kernel was just immensely more accurate in general than SVM. Is the computational expense really just the main thing that's stopping you from using RBF in your solution, or is there something else that it's preventing you from taking the more accurate route?
The more genuine response was that at the time when I really implemented this, the linear SVM was much simpler and was just for my thesis work. So it was just like, just do the simpler approach. But I think the major issue wasn't the computational intensity, but the memory part of it, because using RBF, you'd have to use a large number of the training data set. You'd have to have that in memory. And so that's one major issue. But of course, that can be worked on if I really want to. So.
And quickly, second, are there plans to port this to other like wearable platforms, like ones that already have similar biometric sensors built in, e.g. like Apple Watch, Samsung, that kind of thing?
So the issue with that is that, so that's the reason why this custom built device is useful. So these other wearable devices like the Apple Watch, like you'd have to charge it every single day, right? But this app running on this would need to be charged only after 12 days of wearing it. So this platform is very energy efficient. That's why it's very useful for running on this specific platform. So yeah, I could implement that on, let's say, Samsung Gear or the Apple Watch, but it might only run for a day or two, and you have to recharge it. Yeah.
Yes, with the, I guess, advancement or the advance of new stretchable circuits and flexible circuits with like hydrogels and polymer chemistry, do you see a direct correlation between this between wearable technology and flexible circuitry?
Yeah, so I've seen a bunch of work that has been done in that area in terms of various flexible circuitry that kind of fit on the hands and all that. But yeah, so I guess in the future I could see more of that being incorporated.
Have y'all tried to make any strides towards that at this point? Have y'all tried to make any strides towards that at this point in time?
Can you come again?
Have you guys at your research lab tried to make any efforts towards flexible circuitry at this time?
No. So what we are mostly focusing on is using like external peripherals. Like for instance, the Zephyr that we use, we didn't really build it, so we just use external peripherals and get data from that. So we don't really focus on that.
Thank you.
Yeah. Okay, thanks.
Hello, everybody. I'm a third-year applied math major at RIT, and today I'm going to be talking to you about efficiently computing the piecewise flat embedding for data clustering and image segmentation. So an outline of what I'm going to be talking about, I'm going to introduce you to graph-based methods for image segmentation and our piecewise flat embedding method, how we implemented this efficiently, and our results. So if we take a look at the picture on the bottom of the screen, the leftmost picture is the original image. The three middle pictures are the intermediate steps in the segmentation, and the final image on the right is the final segmentation of the image. So if you're wondering what I mean by image segmentation, keep that rightmost image in your mind. It basically just tries to pull out the different parts of the image into cohesive structures. And if you're wondering why this is useful, for many automatic image techniques and processing, it's important to be able to pull out the important parts of the image as a whole versus just looking at the image. So graph-based segmentation is represented as a graph. So given an image that is n by m pixels, we want to represent each pixel as a node in a graph G and have connecting edges of different weights between those nodes. So for this picture, the 1, 2, 3, 4, and 5 in the circles are nodes, and the lines between them are the edges, and the numbers above them are the weights. So high edge weights signify high similarity between those two nodes, and low weights signify little to no similarity between the nodes. And our goal is then going to be to divide this image into D disjoint classes that contain pixels that are highly correlated within a single class, but are very dissimilar to pixels from other classes. And we accomplish this by cutting the edges between the nodes or the pixels of different classes. The cost of the cut is going to be the sum of the weights that we've cut. So we're going to, with all the weights that we've cut, we're going to sum them all up, and that's the cost of our cut. So when we're making a cut, we want a small cut cost, meaning that we cut the dissimilar links and leave the very similar links intact. So as an example, if this is our graph, here's a possible segmentation. We're going to cut those two edges, and now we're left with two segments, A and B. So when we cut those two edges, we're left with two disjoint graphs, and therefore two classes, A and B. So some notation quick. N is going to be our total number of pixels in the image. D is the number of segments the user wishes to divide the image into. W is our n by n weighted adjacency matrix, which pretty much just holds the weights of the edges. And we can note this is a symmetric matrix since the weight between pixel I and j is going to be the same between pixel j and I. Y is an n by d matrix that will hold the embedding for the segmentation, and that's what we're going to be solving for. And D, I don't know what's going on with this notation, but D is our n by n diagonal matrix, which just has the sum of the weights along the diagonal. So you take the rows, you sum up all the weights, and put it along the diagonal of a new matrix called D. Oh, God. So previous techniques, just bear with me because apparently this didn't email right, and the notation is a little messed up. I'll do my best to explain it to you. So a previous technique that we've looked at is called normalized cuts, and it tries to find an embedding such that we want to minimize the sum of the weights times the distance between the two pixels in our new embedding space. So I know this is a little messed up, but think of it as if we have a high weight and we want to minimize this quantity, we want those two pixels to be really close together in our new space, because then the distance between them will be small and cancel out the big weight. And if the weight is small, we don't care how far apart they are, because even if they're large distance apart, the small weight will take care of that. And this will cause yi and yj to be close together when wij is large. And we have an orthogonality constraint because we don't want the trivial solution of y is just a zero matrix. Okay, so PFE is very similar, but instead of using the L1 norm, or instead of using the L2 norm, we're now using the L1 norm, which is just going to promote a sparser solution, but we're still using the same orthogonality constraint. And the goal of both techniques is to transform our n data points into a space that has a very high dimension to a space that has a lower dimension, where it then is easier to make our segmentation. So advantages of using this technique are that due to a variety of factors such as lighting, distant pixels on the same object might have more differences than neighboring pixels of different objects. So like in the picture below, there's lots of shadows on this pawn, and so it might be difficult to find where the boundaries of that pawn are because of the shadows versus the not shadow sections. So the L1 norm promotes a sparse solution, which makes the embedding piecewise constant or flat, as opposed to having a continuous range of values, which basically means that every pixel on the pawn is going to be drawn together into a very small space, and so we can find that boundary around that a lot easier. And it makes the boundaries more distinct and therefore easier to make the segmentation. So disadvantages are that unlike the L2 norm, there's no simple analytic solution, and so we have to use an iterative numerical scheme to approximate a solution. And it's going to be much more complex to compute the solution, so the running time of the code is going to be much longer, even though it's going to give us a better solution. So the algorithm is since it's iterative, we have to initialize it with something, and we're going to initialize it with the Gaussian mystery model clustering result, which is just another clustering technique. And now we have to do an outer loop that's going to take care of our orthogonality constraint, and we're going to loop through and take care of that. And each time we loop through that, we also have to go into an inner loop. So it's a nested loop that's then going to take care of our L1 norm problem, because there's currently no solution that can do all of that in one step. Well, now there is, but when we were doing this, there wasn't. So now we're going to approximate the L1 norm with a split Bregman algorithm. And the main thing that we were concerned about was that this involves very large and sparse matrices, which makes this step not computationally feasible for large images. So that's why we wanted to come in and take a look at this and figure out how we could reformulate this to make it work better for larger images. So there's two main challenges with the inner loop that we are trying to fix, and the inner loop involves two matrices, M and D, that are used to define two new, even larger matrices. One is called L, which is basically a giant matrix that has D, M matrices along the diagonal. So it's going to be very sparse and very large. And D, which is the same concept, where we're going to have a very large matrix, D, it's supposed to be D tilde, that has these D matrices along the diagonal. These are very, very large and sparse, and to segment an image that is 128 by 128 pixels into 64 segments, M will take 1 megabyte and L will take 64 megabytes to store, and now we want to put these along the diagonal of an even bigger matrix, so it's going to take a lot of memory. And not only that, but we have to do matrix C products with these huge matrices, which also is not going to be very efficient. And we need to solve a linearly squares problem with these two matrices. And the normal equation will probably not show up right, which it didn't. But just keep in mind that these are very large, very sparse matrices, and when you try to take the inverse of a very large, very sparse matrix, you get a very dense matrix. And for the example I just gave, to find the inverse of this matrix that we need to do for the linearly squares would require 8 terabytes of storage. Not very reasonable, so let's try and figure out a new way to do this. So we decided to define a new function that basically takes a matrix and stacks all the columns of the matrix on top of each other. So it takes a matrix and transforms it into a vector, where it takes the first column, puts the second one under it, the third one under that, and makes it a really long vector. So using this notation, we can redefine this L times V product as the vec of M times Y, and D tilde times Y sub V as vec of D sub Y. So now we never even have to explicitly form these very large, very sparse matrices. And also, to find the linearly squares problem, we employ the precondition conjugate gradient method to efficiently solve this, which is basically just an iterative technique to approximate this solution. And we use MATLAB's built-in function to do this with an incomplete Koleski preconditioner. And now we implement this new thing using the same thing that the original authors proposed, which was a 2-stage implementation, where the first stage we run both the outer and the inner loop, which strictly enforces that orthogonality constraint. And in our second stage, we relax the outer constraint and only do the inner loop to make this more computationally feasible. And our average embedding time with these two improvements is between 0.5 and 2 minutes, and it's dependent on the number of clusters, which makes sense because the more clusters we have, the longer it's going to take because our matrices are going to be larger. And the average embedding time without these improvements, as reported by the original authors of this paper, were around 15 minutes. We were able to get this time down significantly with these 2 improvements. And here's some examples of our results. So you can see the original image on the top left, and here are 5 different results for different values of D, which are the different classes. So, for example, the middle top image has 5 segments, so it tries to divide the image into 5 different segments. The bottom right tries to divide it into 25 different segments. This was the same thing that the original paper did, was they did 5, 10, 15, 20, and 25 segments for each image. So we wanted to do that as well to make sure we were getting comparable results. And here's another example. You can see on the bottom, it's starting to pull out some of the mountain, but the top ones, there's only a few segments, so it can't pull it out. And the last image, again, you can see as the number of segments grows, you can start to see more detail, but if you get too large, it starts to pull out stuff that doesn't really make sense, as in D20 equals 25. And our conclusions were that implementing these linear algebra operations and the preconditioning conjugate gradient method, we found that we could get an order magnitude speed improvement, and we yielded similar results as the original algorithm. And if anybody wants to check out our code, it's publicly available on MATLAB Central under file ID 59763, if anyone's interested. And thank you.
Hi. So I was wondering, how do you assign a weight to the pixel edges?
Okay, so when we were doing this, there's a few different ways you can do it. One is using a heat kernel algorithm, or you can look at its 4 nearest neighbors. So I think when we did this, we did the 4 nearest neighbors technique.
And I'm assuming those 4 nearest neighbors also have a specific value. So like the single pixel, is that like an RGB value or a hex value or something like that?
Yeah, so there's many different techniques you can use. You can also, like if you have a hyperspectral image, you could try to apply this to things like that as well. So it depends on like the data that you have.
Thank you.
In my experience with hyperspectral image segmentation, we always used principal component analysis for image segmentation. What are the advantages of this approach over the standard PCA approach?
So PCA is a linear approach and also requires that you have a normal distribution, and that's not often going to be the case, especially with just images. If you're doing something where you're taking data from a population, PCA would be more useful for that. But for this, nonlinear techniques often can yield a better result, especially when your underlying distribution isn't normal or isn't linear. So. Right. Thank you, guys.
Hi, I'm Anisha, and I'm going to talk about my work with modeling traffic during evacuations due to hurricanes. And this I did over the summer at the Media Lab. And I'd like to thank my advisor, Ira Winder, and the rest of the Changing Places group with Kent Larson as a PI for making this possible. So an overview of what I'll talk about today. I'll go through some of the motivation behind working on this project, as well as the concepts in agent-based modeling and queuing theory that we used, and then the validation of our model and some of the metrics we could calculate. So in recent years, we've seen an increase in natural disasters, and this is expected to increase in the future due to climate change, and especially if you consider sea level rise, it makes flooding much worse in disasters such as hurricanes. And this is really relevant for the increasing number of people living in cities around the coast. 60% of cities with a population of over 5 million are along the coast, and more people are moving to cities. So when a natural disaster is severe enough, it can be necessary to evacuate the city. But we've seen a lot of historical problems with evacuations. In Hurricane Katrina, 100,000 people were left behind in the city, mostly from marginalized communities that could have been better served through government interventions if there is a more clear understanding of how government interventions should help. And in Superstorm Sandy, there was a mandatory evacuation order, but even with that, only 49% of people left. And surveys afterwards saw that most people didn't understand the risks of remaining in the city. So how do you present information about evacuations to government officials and to the public to have better overall results? In order to plan for evacuations, you need to understand what will happen, but there's such little data, empirical data, about the unique traffic patterns during evacuations. So our model attempts to fill that hole with giving more information so you can better predict evacuations. The main question we were looking to answer was, during a hurricane evacuation in Massachusetts, how would the traffic conditions change over time? And can a simulation of the evacuation help to identify vulnerable regions? So our system for this, looking specifically at Massachusetts, we looked at the areas that would be affected by hurricanes, that would be flooded in different categories of storms, and we overlaid that information with census data to figure out how many people live in each of those areas. And those went to create the agents in our model. And then we put these agents onto the network of roads in Massachusetts so we could model traffic, which we represented as a graph where the roads are the edges and the intersections between roads are the nodes. And all this went into our simulation. We had to make a few abstractions, which in the future we can go and address further, but we assumed that everyone would take cars and that everyone starts evacuating at the same time, because in order to determine, we need more data in order to determine how many people would actually take cars, and there's a whole social science between when people will choose to evacuate based on what information is present. So for now, we've left them as is, but this is something we could incorporate in the future. We also assume that cars don't choose alternative routes due to congestion in the process. Again, this is something we can add with more data, but this follows closely with, if people follow pre-planned evacuation routes, there probably won't be navigation in the process. We model this using agent-based modeling, which is where you have agents, in this case cars, treated as separate entities. So we keep track of the location of every car separately, and in more complex models, you can also keep track of the driving behavior or the type of car or other things like that. And the basis of agent-based modeling is that you have simple rules that govern interactions between two agents. So a car can drive forward until it comes to the car in front of it, at which point it can no longer move forward. And when you have many agents in the model, you have a complex behavior that emerges out of these very simple rules. But one of the drawbacks to agent-based modeling is that it can be very computationally complex because you have so many different objects that you're keeping track of. And since we were looking at a regional scale, we needed to find a way to simplify this a little bit. And we did that using queuing theory, which is studying waiting in lines. And in this, we represented each road as a queue or line of cars. And when a car enters a road, it gets in line at the end of the line. And over time, it moves up through the road, increasing its position in the line as well. And when it gets to the front of the road, it can then move on to the next road because there are no more cars in front of it. And this also inherently models congestion, which is really important for modeling evacuations because there's so many cars on the road. So a road, once it reaches its capacity for how many cars it can hold, becomes full and will not accept any more cars onto the road until there's space. So because of that, cars will have to wait on the adjacent roads, which will then build up congestion in those areas and thereby spreads congestion around a region. So this is a video of the simulation that I had in the visual interface. Here we have part of Massachusetts where the blue lines are the roads and the white spots are the population centers, which indicate the regions that people will need to evacuate from, and the density shows how many people need to evacuate from there. So let's hope this works. Yeah, so this is really glitchy on the PowerPoint, but it's much smoother in the actual simulation, showing the agents, which are the cars, moving away from the coast and to destination cities. And they chose the destination based on randomly selecting between nearby cities that are out of the hurricane area. And this is because cities have the best potential to absorb an influx of people. And they did this using simple path planning, using Dijkstra's algorithm. And each dot represents about 200 cars just for the ease of visualization. I'm sorry that it's so glitchy. It is usually not like this. And as they move away, you can see some yellow and red regions build up on the screen, and this indicates congestion of the road. So as a road is congested for a longer amount of time, it becomes darker and redder, so that as the cars leave, we can start to identify areas that might be potential problems for congestion. And you can also select between different categories of hurricanes and zoom in and out to see the behavior at different scales. So we were able to validate our model in free flow conditions, that is with no congestion, by looking at a set of points as an origin and destination and calculating the time we think it would take for a car to get from one to the other, and then comparing that to the prediction from Google Maps navigation. And we found that in free flow conditions, we were within 20% of the Google Maps prediction. The main sources of inaccuracy were with navigation. Unfortunately, we were not able to validate this for congestion conditions because there's such little empirical data from past evacuations. However, other queuing models have been shown to be pretty accurate in modeling congestion through other studies, and we've used a fairly standard implementation of the queuing model, so we're fairly confident that we have a reasonable model. This is a graph of our estimates compared to Google navigation estimates in free flow conditions. We have 6 cases represented here, and the time the y-axis is the time we think it will take to get to the destination. Cases 1 and 2, the blue diamonds are the Google Maps prediction, and the white X's are our prediction. The first 2 cases are in the city, and that's where we have the biggest source of error because we did not model traffic lights and other city conditions because we were looking at such a regional scale, so that's understandable. In the highway cases, we were much closer to the Google prediction, except in case 4, which is where there is a difference in the navigation route that we expected versus what Google Maps had calculated. So with this model, we can now take metrics from that and identifying vulnerable regions and also quantifying the distribution of travel time for each car. So this is an example of a heat map that's left behind after the simulation. We can see that there's a really dark red region around the Boston area, which is expected because there are just so many people trying to leave the area. And another place to point out is from Cape Cod to the rest of Massachusetts, there are only 2 bridges, so a lot of traffic backs up there. And both these areas are causes of concern because they're both in areas that would be flooded by hurricanes. So if people are still in those congested regions during the storm, it could be really dangerous. We can also look at the time each car spends on the road from its origin to destination and graph that as a distribution. So here we see that most cars get to their destination within 2 to 4 hours, which is pretty good, but there's still a number of cars on the road much after that. And we can compare the shape of this distribution to other runs of the simulation with maybe different categories of hurricanes or after implementing different types of policy interventions to see how things that we do can affect the overall situation for the evacuation. So in conclusion, we were able to implement the queuing model in Massachusetts for hurricane evacuations, and we presented this information with an intuitive visual display that you don't have to be an expert to understand. And from that, we're able to qualitatively identify vulnerable areas and regions that congestion might be a problem, but we do need to do more work in order to validate this model in congestion conditions. And future work for this would include implementing interventions. So what would happen if we evacuated different regions first? What if we got people out of Cape Cod before the storm hits? And how would that change the overall congestion in the system? Also looking at public transportation and all the people who don't have cars and looking at different methods to get out of the city. And we could also evaluate government assistance, government emergency assistance and programs and see how effective those would be. So overall, we've created a baseline model that evaluates a baseline traffic level, and then we could evaluate interventions using this. So thank you. And any questions? There's. Thank you. I think there's one down here.
Small question, but did you assume one person to a car, or like did you take an average, assuming like family cars and things like that?
Yeah, I assumed carpooling and family cars, so I assumed 4 4 people per car, because ideally people can also help their neighbors get out if their neighbors don't have a car. So it's being optimistic about human nature, but hopefully that's what would happen. Okay, well, thank you.